Okay, so we're going to look at Chapter 2, Graphs and Networks. Thank you again for Dr. Frost and Andrew Blackett. So as you know, we've already done algorithms. We're moving on to graphs and networks. So a graphs consists of points, okay, but we're not going to call them points. We're going to call them vertices or nodes. I'll flick between the two, and they're connected by either edges or arcs, okay? So if a graph has a number on the arc or the edge, it's normally called weighted, okay? And it's called as a weighted graph or network. So these are both graphs here. And why are these both graphs? Does anybody know why these are both graphs? Okay, so here we have essentially points, vertices or nodes, which are connected by lines, so are edges or arcs. So for example, on the EasyJet one, we can see here that our nodes are countries, and then our edges essentially, or arcs, I'm assuming these are the distances. If they had distances on, they would then be weighted. Here, our nodes are people, and this is a family tree, isn't it? And our edges connect how they are related in the family tree. So, we're going to look at modelling with graphs. So, weighted graphs are not drawn to scale normally, so it wouldn't make sense. For example, we can see here that this 60 line is possibly the same or slightly bigger than this 150. They're never drawn accurately, okay? So do not be afraid by that. So the network shows the length of time in meters per second for a ping between different computers on a network. Write down the time it would take for computer B to ping to D. So we're going to have a look at B, and to get to D, it's going to take 50. Now, there are other ways we can get to D, but at the minute, we're just going to choose the one that's straight away. Write a list of the computers which are directly connected to computer E. If I have a look at E, directly connected, we've got A, B, and F. Those are the ones that are directly connected. A, B, and F. It then says, list some of the routes a signal could take from the server to computer F. So if we're at the server and we're going to F, some of the routes we could have A, E, F. Okay. We could also have from the server, sorry, I should start with S. Then from the server, for example, we could go BDF. And then from the server, we could also go CDF. There's another way we could go server BEF. We could go server ABDF. We could go, there's a few multiple ways we can do. As long as you can understand that there's multiple routes, that's perfect. Does anyone have any questions with this at all? If you do, there are some questions available to you. So the vertices or nodes here, as we can see, are represented by letters. And what we have available is A, B, C, D, E, and F. Okay? And this list is sometimes called the vertex set. So, the types of edges and arcs that we have AB, AF, AC. So we're going to write that on there, AB, AF, AC. And then I know we have BC, but BA, but I'm not going to rewrite that again. We've got BC, BD, and we have CE and DE. Okay, and this list is sometimes called the edge set or arc set. So, what we have is sometimes we can draw subgraphs of this graph G. So this graph is G here, and we have subgraphs. So you can see DECB is a subgraph. All we've done is we've removed the nodes A and F and the arcs adjoining them. Okay, here's another subgraph. What I would like you to do is draw another one for me, please. Okay, so another subgraph could be, we could have F, A, C. Okay? So now we need to move on. There is a lot of terminology that we need to know so that when I'm talking throughout the course, you're going to understand what's going on. So the degree or variance or order of a vertex is the number of edges that connects to it, okay? You'll normally hear me say degree or order. I won't use the word variance, okay? So if we look at A, from A, we have exactly 3 arcs. So that has a degree of 3. For B, we also have 3. For C, we have 3. For D, we have 2. For E, we have 2. And for F, we have 1. Okay? So if a vertex has an even degree, we say it's even. And if it's got an odd degree, we say it's an odd vertex. Okay? So here we go. Test your understanding really quickly. This should probably take you 10 seconds. Off you go. Okay, so nice and simple. So we've got 2 for A. For B, we've got 4. For C, 1, 2, 3, 4, 5, even though this arc is back in on itself. And then for D, we've got 3. So we have walks, paths, trails, and cycles, okay? So a walk is a route through a graph along edges from one vertex to the next. So for example, to go on a walk, we could do F, A, B, C. Okay? F, A, B, C. That would be a walk. A path. Okay, so a path is a walk in which no vertex is visited more than once. So I'm just going to go back to the walk. A walk, we could, if we wanted to, go C, E, A, back to B, down to D, if we wanted to, okay? But a path is a bit different because in a path we can only, so F to D, E, and then up to C, but we wouldn't go B and then back to D, okay? So a trail is a walk in which no edge is visited more than once. Okay, so what I've done here, so this path could also be a trail, okay? A cycle is a walk in which the end vertex is the same as the start and no other vertex is visited more than once. So for a cycle, nice and easy, we could have F, A, B, C, E, D, F. Okay, that's a cycle. And then a Hamiltonian cycle is a cycle which includes every vertex, okay? So this cycle that we've just created is also a Hamiltonian cycle as well because every vertex is connected. But we can have a different type of cycle if we wanted to. So if I do a different type of cycle, my cycle could just be F, A, E, D, F. That's a cycle, but it's not Hamiltonian because in that one we didn't include B and C. Okay, so we are going to test our understanding of this. So a walk, again, we can go A, B, C, D, B, F. Okay, we've taken a walk. And when we take the walk, we can visit multiple vertexes. Now, a path, we cannot visit the same vertex. So a path could be F, A, D, B, C. Oops. Okay, and this will make more sense as we go through. A trail, No edge is visited more than once, so we can't do double edges. A cycle we could just do A, D, C, B. And then a Hamiltonian cycle is where every node needs to be visited, okay? So, to do that, we could have literally B, A, F, D, C, B. Nice and simple. Okay, so two vertices are connected if there is a path between them. A graph is connected if all the vertices are connected. We can see here that this is not a connected graph because E is not connected to the rest of the graph. Really easy to fix. We could just connect it, okay? So, let's have a look at different types of graphs. Here we have some different types of graphs. So which ones are connected and which ones are not connected? If we have a look at the first one, every node is connected by a vertices. So this one is connected. Okay? Again, every node here is connected by some vertices. If we look at this one, E is not connected to the rest of the graph. Okay? This is a not connected graph. And then for the last one, we can also see that C doesn't actually have any arcs. This is also not connected. So nice and simple for everyone. Okay, a loop, what we've seen earlier. This is a loop, okay? And we would have a loop in the network, okay? Sometimes we'd have a loop in the network if, for example, this was a telephone network. We might, they can make multiple phone calls simultaneously. That's why we'd have a loop. And we can see here we've got multiple edges, and that's completely fine. So, simple graphs. A simple graph is a graph where there's no loops and there is at most one edge connecting any pair of vertices, okay? So we can see here we've got no loops and there's only one edge connecting vertices. This is called a directed graph, and the reason why this is a directed graph is because we could only go in the direction from A to B. This is like, with vectors. Vectors are directed graphs because we can only go from A to B in this direction. A, we can go A to F, F to A. We can go A to B, but we cannot go B to A. Okay, this is what helps us when we're looking at one-way systems in streets. So, the Handshake Lemma. So, in any undirected graph, the sum of the degrees of the vertices is equal to 2 times the number of edges as a consequence. The number of odd vertices must be even. The result is shown as the Handshake Lemma. So, if we have a look on this graph here, okay, how many odd vertices are there? So, even A, 1, 2, 3, 4, 5, that's odd, 1, 2, that's even. 1, 2, 3, 4, 5, 6, 7. Okay, so here, D and C are odd. So we've got 2 odd vertices. Okay. So, they're saying that there will always be an even number of odd vertices. So if we have a look at the second graph, I have 1 odd, A is odd, B is odd, C is odd, and D and E are even. Okay, so I've got 4 odd vertices. So, your challenge now. Can you try and draw a graph with an odd number of odd vertices and see what happens, please? Okay, so pick 4 nodes and see if you can connect them in any way so that you have 3 of them, or at least one of them, have an odd number of vertices. Off you go. Yeah, so as we can see, it's not possible, okay? And I think it's really hysterical that it's not possible, because you'd think, yeah, of course it would be. But there's always an even pair of odd vertices or nodes, okay? No matter what I try to do here, you can see I've got odd, odd, even, even. And if I try and add a few more arcs, maybe put one here, what I end up having is even, even, odd, odd. Okay, there isn't a way to do it, which is fantastic. That's what I love about this. So, here are some definitions that you need to understand, okay? And I will be testing you on these next week. Now, what we are going to have now is a few more definitions, so hold on. Okay, this is a bush, okay? It's got no relevance to what we're doing today, but, okay, we are going to be looking at a new definition, which is called tree. So a tree is a connected graph with no cycles. We can see here there's no cycles. This is a tree. This one has a cycle, as you can see, B, C, C, B. This is a cycle here. So this is not a tree. A tree is a connected graph with no cycles. So not a tree. Normally in the exam they will say to you, define a tree. And you will have to write a tree is a connected graph with no cycles. We can see this one is a tree. And we can see this one is not a tree because it has a cycle. Okay? So a spanning tree is a subgraph which includes all the vertices and is a tree. Okay, so all the possible spanning trees of G are, we always start with all the nodes. So we have A, B, C, D. Okay, so let me see if I can actually do. Oh. Okay, so as long as they're connected using the roots that we can have. For example, A and B, B and C. And then we could have A, D, D, C. No, that doesn't make any sense. No, there we go. Right, A, D, B, C. Okay, this is a spanning tree. So it's a subgraph of the original graph, but does not have any cycles. We could do the other way with A, D, B, C, where we have A to B, A to D, and D to C. I can only use the arcs that are provided to me. We could also have A, D, B, C. I didn't use that one. So that would be A, D, B, C. Okay. We could also have A, D, C, B. Yep, didn't use that one either. A, D, C, B. Okay. We could have DA, DB, DC. DA, B, C. A, B, C, and D. And then finally, we could have, let's get a different colour. A, B, C, D, the other way. A, B, C, D. Okay, how would I know if I've drawn all the possible spanning trees? Okay, next type of graph is a completed graph, okay? So, every vertex is directly connected by a single edge to every other vertex. So we can see here in a triangle, from this vertex we can connect to here, connect here. We call them K3, okay? This is K2, K4, everyone's connected. So if we were to draw K5, step 1, we're going to draw 5 vertices, okay? And if every single one has to be connected, we're going to draw a really nice shape. This one's connected to this one, to this one, to this one, to this one. Okay, then I start. This one's connected to that one. It's already connected to that one. And then you can see what's going to happen. Every node has an arc connecting to the other node. And you can see it's really beautiful. Okay, can you please draw for me K6? So this time we're going to have 6 vertices. And can you draw the completed graph, please? K6. So here we have the complete graph, K6. So if we have a look, for 3 vertices, we need 3 arcs. For 4 vertices, we need 1, 2, 3, 4, 5, 6 arcs. For 5 vertices, we need, I'm going to have to colour these in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, for 6 vertices, oops, I did not mean to do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No, I already did that one. 15. Did we get 15? I wonder, can anyone spot a pattern? So using the pattern, I wonder how many edges are required to draw K10? How many edges are required to draw K10? So if we had K7, K8, K9, K10, if you think I added 5, if I add 6, I get 21. If I add 7, 28. If I add 8, 36. And then if I add 9, I'm going to get 45. So there'd be a total of 45. But then if I said to you, what's K21 going to be? I can't just expect you to sit there and do all this. Okay, how about Kn? So there is a formula, and the formula is a half n minus 1 edges, okay? Anyone who can prove that to me is going to get bonus points. Okay, so moving on, here's a typical exam question. A table tennis, tournament is designed so that every player plays each of the others. If there are 15 players, how many games would be required? How many tables would be required to play the tournament in the minimum possible number of rounds? Okay, so essentially, I'll give you that formula again. Half n minus 1, okay? Give this a go. It's K15, so to work out exactly how many rounds, I'd have a half of 15 times 15 minus 1, which is 7 times 15, 105 edges, okay? So therefore, that would mean there'd have to be 105 games. Now, as you can see by that lovely display I've just done, each player would have to play 14 games. So if there were 7 tables, we could play this in 15 rounds. That would be the minimum. Okay? So if 7 tables, then 15 rounds. Okay, and you could see that by this lovely little drawing, okay? We'd keep going round. So, moving on. Okay, isomorphic graphs. You can see here, okay, that these two graphs are isomorphic. They may look different, but essentially the graph is the same. Okay, it's the same information, they just look different. For example, A is connected to F, C, and B. And here, A is connected to F, C, and B. Okay? F, C, B. That's what A is connected to. B, C, F. That's just drawn slightly differently. Then we can see B is connected to D only. Here, oh, and A, obviously. B is connected to D only and A. And then we can see that D is connected to E. And here, D is connected to E. Basically, they are the same graph. All they've essentially done is this point D, they've moved it over here, so it crosses over. That doesn't matter, though, that they cross. It doesn't mean we can go B to this point and then switch to A. That doesn't work like that. You can only change if it's a node. Just because it crosses, you can separate that. We could essentially move this point up here if we wanted to and draw it slightly differently. So isomorphic graphs have this same information, just drawn slightly differently. It's like when we had similar shapes. You know, I don't know if you remember back in year 7, you might have a right angle like this. And then they draw it this way. Okay? They are the same, they're just drawn. One's upside down, one's not. So, are you ready? Please can you identify the two isomorphic graphs below and justify why they are isomorphic? So is 1 isomorphic to 3? Is 1 isomorphic to 2? Or is 2 isomorphic to 3? You need to justify your answer. Off you go. Okay, so 1 and 2. Now, at a glance, why could that be? I can immediately see that B here is only connected to A, D, and C with 3 arcs. Whereas on number 1, I've got 4 arcs, and here I've got 4 arcs. That would lead me to believe, if I knew that 2 were definitely isomorphic, it is 1 and 2. Well done. Okay, so for this part of the chapter, we've learned about trees, spanning trees, complete graphs, and isomorphic graphs, okay? Again, if you need more help on that, please use the book. Okay, last but not least, and then we will be able to move on to prims, Kruskals, and Dijkstras, which I'm really excited about once we've got all the terminology. So, representing graphs using matrices, okay? So, what we're going to do is we're going to do 2 things. Number 1, this is a matrice, and we're going to draw a graph, and this is a graph, and we're going to draw a matrice, okay? So, in a non-weighted graph, so these graphs, again, you know, aren't weighted, each entry describes the number of arcs joining it. So for the first one, I can see I've got 3 nodes, A, B, and C. So I'm literally just going to draw A, B, and C. Now, there's no right or wrong way to do this, okay? But when I think of A, B, and C, I think of this. Then I have a look. From A to B, there's 2 arcs connecting. So 1, 2. From A to C, there's 1. Brilliant. Okay, so that first row is done. From B to A, there's 2. I already did it. B to B, 0. C to B, 0. A to B, 1. Already did that. B to C, 0. C to C, 0. Okay, perfect. I've drawn it. Wonderful. Now, that I've represented using a matrice, okay, the graph. Now I have a graph, and I'm going to use this representing a matrice. So from A to A does not have a loop, so 0. From A to B, I can see there's 2 arcs, okay. From A to C, there's 1. And from A to D, there's also 1. Okay, now what I love about these kind of tables is, you know, there's symmetry. So this is also 2, 1, 1. Okay. From B to B, 0. B to Z, C, blah, 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 C, 0. B to D, 1. Okay, and again, I know that's symmetrical here. C to C. Okay, there are 2. 1 here, 1 here. Okay. Because I can start here and come back round, or I can start here and come back round. From C to D, 0. And again, that's symmetrical here. And then from D to D, 0. And there we go. I've represented this graph in a matrix. Now, this time it's slightly different because we have a weighted, this is weighted, okay? So, if I draw A, B, C again, this one doesn't represent the number of arcs, this just represents the distance. So from A to B is 23. From A to C is 10. A to B, 23, we already did. B to C, 14. Okay, and then we've already done all those. Now, for this one, slightly different, but still the same. A to A, 0. From A to B, it's 8. From A to C is 10. And from A to D, there is no directory. Okay? And again here, actually, don't put 0. That would imply that just put no directory. And again, there's symmetry about that. Then, B to B, nothing. B to C, 23. B to D, 14. And again, we've got our symmetry. C to C, we can go from C to C, it's 5. Okay, C to D, 7. And again, we have that symmetry. And then D to D, we don't have anything. Nice and simple. Okay, one more type. So, directed distance network. So this won't be symmetrical because it's directed. The other ones were symmetrical because we could go back and forth. For this one, we can do AB. So here, A to B is 2. Okay. But B to A, we can't do it. Okay, so that's what I mean by that. So first we're going to start drawing the diagram, A, B, C, D, E. Now, I always, for some reason, and you can do this how you want, I always, A, B, C, D, E. I always just draw this in a circle. It may not be the best way, but it's just the way I always do it. Okay, and it's the same with when I've got 3 vertices, I just draw like a triangle. So A to A, nothing. A to B is 14. But I can see there's no B to A. So that must mean that's directed, and that is 14. Okay, so watch out for that. A to C, nothing. A to D, nothing. A to E is 2, but I can see down here that E to A is 2. So that means there's no direction there. Perfect. Okay, and this is 2. B to B, nothing. B to C, 8, and C to B is 8. Okay, so that's 8. And there's no direction. And then there's nothing, 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 nothing. C to D, no, there is no C to D. D to C is 12. Okay, and that's in this direction from D to C. So, remember, because we always read from the rows across. Okay, so that's done. And then E to D is 6. E to D is 6. And that is in this direction. Okay, And then similarly, we can go A doesn't go, A just goes to B and D actually. Okay, B doesn't go to B, B goes to A, but it's the other direction, so it doesn't count. B goes to C for 3, and B goes to D for 5. C goes to B for 3. C does not go to C, and C does not go to D. D goes to A for 11, D goes to B for 5, and D goes to C for 7. Nice and simple. Okay, so if you need some help with that, we are going to go over all of this when we do prims, kruskals and dijkstra's, as well as the travelling salesman. Okay, but if you need more, please feel free to do some questions in the book. Right, this chapter's done. I know it was a little bit boring, but lots of definitions that you need to learn that you will be tested on next week.